gonna come out okay. Okay, so what I'm gonna do is we got 4 chapters basically that cover statics. And so I'm using this FE Civil Practice Problems, has 4 chapters. There's a 5th chapter which probably fits actually a little bit better into mechanics of solids or something. It's on the indeterminate. So I'm not going to do anything on that. And what I did was I kind of went through and picked a variety of problems from each of the chapters so that we can get a variety of problems, and then we can always come back if you want to see more of a certain kind. Okay? So, oh, and then I always forget which computer I'm running things on. Okay, so the first chapter was Systems of Forces and Moments. It's chapter 21. And so I picked problems 3, 4, 5, 6, and 9, and then a question mark on 14. Oh yeah, 14 is probably not is a good one to do too. Okay, so the loading shown requires a clockwise resisting moment of 20 Newton meters at the support. Okay, so what that's telling me is, let's get some markers out. It's telling me that here at the support, I need to have 20 Newton meters. Okay, the better way to say that is this wall support is going to provide 20 Newton meters because of all of this loading. And so we can then look at this loading, say it has to be equal to 20 Newton meters, and solve for that force F. Okay, does that make sense to everybody? Right, let me back up here for a minute. In a kind of more normal statics point of view, we would have given you this force, and when you were taking the class, we would give you this force and ask you what were the reactions at the wall, what were the support reactions at the wall, okay? And you would have a resisting moment and then a force in the y direction. They're coming in and saying that resisting moment is 20 Newton meters, so let's figure out what that F is, okay? So we're going to sum the moments, and they end up summing them. I'm just going to call this O. So we'll sum the moments around O, and they've got to equal plus 20. And so we're going to go, I like to use this clockwise. All of a sudden I realized that when I was writing that stuff up. Didn't look physically what's going on, right? If this is pushing down this way, causing a moment this way, the wall has to be resisting that. So that's 20 Newton meters. So standard is to call this the positive direction. Counterclockwise is positive. So that's usually, I kind of just usually keep that. Okay, so then we just crank on through. Force times distance, right? Force times lever arm. So I got a 15 times 1.5. Plus F times 1.5. Plus 75 times 0.5. And then I just added in on this side, that's, sorry, the way I've set this up. I'm sorry, I even worked through all of these. I'm going to call this the sum of the moments has to be equal to 0. So then I'm going to put my minus 20 in here. Is equal to 0. Does that make sense to everybody? And then I just solve for that force. We'd end up with force is equal to 20 minus 15 times 1.5 minus 75 times 0.5 over 1.5. Hey, how's it going?
Good, how are you?
Good. And I got a negative number, negative 26.67 newtons. That negative means it's got to be opposite the direction that we put it in, so it's actually going up. So it's this one. Okay? Okay. This one, I don't think there's any way to rule out any of those numbers. I mean, just looking at it. A couple of these problems, I think there's ways to kind of rule out, if you can't get an answer, to rule out certain ones and at least guess between likelies. I don't think you can on this one. Okay, any questions? Okay, holler if you got questions. Okay, so this one we have a benzene, and it's acted upon by a moment and several forces. So there's my moment and all my forces, and it gives us a value for the moment. And we want to come up with the value of F and the distance x that will maintain equilibrium on the beam. Okay. So again, what you're going to be doing is some of the forces. Because for equilibrium, we've got some of the forces. In this case, I only have forces in the y direction, so I don't have to worry about x. And I've got some of the moments equal to 0. So let's do some of the forces y first. So I got a minus 60, plus 10, plus 20, plus 10. Oh, that's a really ugly 20. Sorry, I was looking at the same time I was writing. Maybe I should write those bigger too, so they'll show up a little better. Okay, minus 60, plus 10, plus 20, plus 10, plus F is equal to 0. So what have we got? Minus 60 plus 40 is a minus 20. So F is going to equal plus 20. Okay. If I come up, that's already going to knock out 2 of those. Okay. So if you went at least to the next one, you could, at least if you couldn't get the next part, you could at least guess between C and D. Okay. All right. So some of the moments. All right. Now you're free to pick any point you want to some moments around. So you might as well pick one that works for you. And if I pick D, I knock out the 10 Newton and the 60 Newton. Okay. And again, I'm going to come in and do positive is counterclockwise. So 60 and that 10 go through point D. Got to put that in there now. So I'm going to ignore those. So I got 20. That's going to give me around here. That's going to give me a positive 20 times 0.2. Plus 10 times 0.2 plus x plus F times 0.4 plus x. And then I can't forget to put this one in, and that's clockwise, so that's a minus 20 equals 0. And I solve for my x. And we should, I think I checked most of these that I got the right answer, but you guys should double check me. I got x is equal to 0.2. This one after this. Oh, okay. All right, for the members shown, let me erase. The 700 Newton meter moment is applied at point B. And then it says if the member is pinned so that it rotates around point B, what counteracting moment must be applied at point A to keep the member in equilibrium? Okay, so let's go through a couple thoughts here. The first thing is, remember, pins don't, pins only, oh, sorry, did we need where we were?
I was just asking about the last one. I got
Okay.
0.3 for X when I solved it through, so I think I did something wrong.
It is, you got 0.2. Yeah, I got 0.2. Okay.
Yeah.
Okay, cool. Okay, I've lost my train of thought. Oh, so this is pinned so that it rotates around point B. That's all that this is indicating, okay? Pins don't transmit moments. Remember, when we think about support reactions, we want to think about what the support prohibits. And so a pin will keep this from moving in the horizontal and moving vertically, but it allows free rotation, okay? So, and then it says what counteracting moment must be applied at point A to keep the member in equilibrium. Well, technically it doesn't even have to be at point A, it could be anywhere, okay? We just would have to apply it. So again, what I want to do is I want to set the moments to be 0. And I picked point B, and I'm trying to think why I picked point B. Oh, I know why I picked point B. So also, remember for these things, we have a force here that's not aligned to the horizontal or the horizontal or the vertical axis. So we can break this up into components. And that the member behaves exactly the same way. And the long hypotenuse for this triangle is going to be 13, okay? So I can come in and replace this with a force here that is going to be 4/5 times 200, and one here that's going to be, 3/5. I should make that a little bigger. 3/5 times 200. And here I can replace this with 5/12 times 300. And this way, not 5/12, 5/13. And this way with 12/13 times 300. Okay? So I picked to sum around B because I knocked out one of these and one of these, and I just thought that was easier. Okay. All right, so again, I'm going to sum the moments. Sum the moments around B equal to 0. This component has a line of action through point B, so it doesn't contribute. So I have a contribution from this one, it's negative, so I'm going to have a negative 4/5 times 200. Then I come down to this one. This is going to contribute counterclockwise, so that's positive. It is, remember, extend the line of action. So it is 2 meters above here, so I got plus 5/13 times 300 times 2. Then I've got this one, the vertical component, extend the line of action. Distance between point B and the line of action is 4 meters. So, and also this one is also going to be counterclockwise, also positive, plus 12/13 times 300 times 4. And then I have this one. Right, this one, the 150 line of action goes through point B, so it contributes no moment. That leaves me this one, that's clockwise, so it's negative 150 times 4. And then I got to put in that moment of A, because when I add that in, that's going to give me my 0. And I solve for moment of A. Yeah.
Wait, sorry, so, the 4/5 times 200, why is that not multiplied by 8?
It should be, thank you. Yes, times 8.
And then why wouldn't the moment of A be multiplied by 8 as well? Because if you're sending the moment around B and you're trying to.
No, because the moment at A is already, it's a moment, it's already in Newton meters. That's the unified way to say it.
Cool.
Yeah. Okay.
So if there was a moment around C, you would have just added it as.
Yeah, so if in this problem, let's suppose that they had a moment here, like this of, I don't know, 100 Newton meters, and had the same problem, then I would put in plus 100 plus the MA.
Okay.
Yeah.
Thank you.
Yeah. I got 1241. And I've got counterclockwise. That's what I came up with. I'm waiting for all those calculator fingers.
The basic one?
Yeah, I know. It's really hard to go back to those after the, yeah, I know. Okay. Okay. Okay, so this one, we have an overhanging beam. It's overhanging because we've got the hinge down here, roller here, and we've got a bit that's hanging off the roller. And it said the moment is removed, so this 2.5 Newton meters is removed, and it's replaced by a couple consisting of forces applied at points A and C. Okay, so I'm going to pull this off, and I'm going to put a force here and a force here. And I want to know what the magnitude of the forces are that constitute that force couple. So remember, a force couple is, you put it here, I have a force in this direction. I don't know why I started to draw that force like that. I have a force like this and a force like this. That's F. This spacing is D. And the magnitude of the moment for the couple is force times whatever the spacing is between the two of them. Okay? The beam can't tell if there's a difference between having this moment applied or having two forces applied at the right distance. So what I need is 2.5 Newton meters to equal the force. Now they told me the distance because they said at points A and C. So that's 0.1 plus 0.5 plus 0.2 plus 0.4, which is, what is that? I'm looking now. 1.2. 1.2 meters times that force. And I think you're going to get that 2.1, right? That 2.08 or something. You're just looking at the numbers. Everybody good with that? Okay. The next one I was going to do was number 14. This one's looks a little worse than it actually is. What we have to remember is that we can take things apart. So here we have this hinged object and it's pinned at 2 points. So remember, pins are going to exert a horizontal force and a vertical force. So my support reactions would be a force up and this way and up and this way. I can oh yeah, sorry, I had to read the problem because I couldn't quite remember what we're doing. So we're interested in what's happening here, okay? So let's go in and look here. I would have to have, I'm going to call it A sub x and A sub y. And because that's a pin, it doesn't support a moment. So the moment that will be supplied by the support is 0, okay? Here you're given two options, one with a 5,000 and another one with a 5,000. Those are not possible. So I'm going to pull those out, okay? If I sum the moments around C, then I can see that A sub x is going to go through there. The forces at C, should maybe just put them in. We don't need them, but just to remind you they're there. There, if I sum the moments around C, this line of action, that line of action, and that line of action all go through C. So they all contribute 0. So that will let me figure out what A sub y is. Okay, so I can sum moments. Actually, do we need to even to do that? Yeah, because they gave us different y values. So some of the moments around C equal to 0. okay? A sub y is gonna be clockwise, so that's a negative. So the negative a sub y times 10 plus this is gonna be clockwise, that 1,000 newtons, and that line of action is 5 meters above. I'm guessing we're in meters. And so that gives me a value for a sub y. And I got 500. Which actually picks out B, so you don't even have to find f sub x. But if you want to go in and find f sub x, let's say you didn't see that, for some reason you didn't realize that, you would go in and you would draw basically kind of a free body diagram for this piece. So you would have up like this. That's not the best looking thing. Oh, sorry, not a sub y, a sub x. You can see what I've written here. So this is a sub y. This is a sub x. And here you would have that 1,000. And I'll just pick it this way, b sub y and a b sub x that were coming from this object. But if I sum my moments around b, all of those will drop out. I've already figured out what a sub y is. That'll let me figure out what a sub x is. That makes sense to everybody? Okay, you don't need to do that, but you could. Or if you were like me, I'd probably just start going and do it before I really think about it. Good? Okay. All right, so if we have a little time left at the end, we can come back and do that problem with the traffic signal one. It's actually fairly straightforward, but I think it's right before 14. It's really not bad. It's just understanding I have not seen something, what was it that was weird on this one? Oh yeah, they gave the weight as a pressure, which to me was very odd. But we can do that. But I think from what we've done so far, if you read through that one, you'll understand what they did. So it's more moments. It's just moments with some funky things thrown in. Okay. So chapter 22 is trusses. And they picked some doozies. Okay, so the first one I picked was actually problem 4. And I picked this one. In truss problems, one of the first things you have to decide is based on what they're asking you to find, do you need to find the support reactions first? Okay, so because I've also set up to do, I think, 2 and 3. So let me kind of point out what I'm trying to say here. So in this case, we're supposed to find the force in the diagonal member of BA, okay? And what makes the most sense is to take and do a cut here, a section there, and then look at that top section. And if I do that, I don't need to know what happens down here at the ground at this point and this point, okay? If I go to the next one, like this one, in this one, we're asked to figure out the force in AC and BD. And in order to get any of those, if I make a cut here, I still have to find this F1. If I were to do a pin analysis here, I still need to find F1. There's no way I can approach this problem without figuring out those two support reactions. Okay. So that fourth one is, in a lot of senses, the easiest one to do. Or maybe take, well, I don't know, however you want to think about that. Okay, so we're going to do a section here. I wonder if I should have moved that up. That's all right, we'll see where we are. Okay, so I like to draw these things and I always put a little squishy there on the end to tell me that's where I cut it. And then I always draw these in tension. So I would come in, and let me just use the same notation I did. This one, I kind of made up some notation. So I just call this one force here, I called F1. This force here, that's the one I want. So I actually came in and called that force BA. And then I came here and called this one force 2. And I am going to need an angle. And I came in and used, doesn't really matter, but I found this angle right here. And so that angle opposite is 20 over adjacent is 15. So that angle is going to be, I got 53 degrees. Oh, that's why that looks, that's a 345 actually. Well, since we found the 53, we'll just go with it. Okay. All right, so at this stage, I now have kind of a standard equilibrium problem. I can do some of the forces equal to 0, or some of the moments is equal to 0. Some of the moments are on some point. And if, remember, the point does not actually have to be on the axis, or I'm sorry, on the three-body diagram. So in this problem, it's awkward because this FBA, the one they want us to find, has components in both horizontal and vertical. So the way I approached it was I took the sum of the moments around point A, which is not on my section, and that dropped out F1 and FBA and let me find F2. Once I find F2, then I know that the vertical components F2, F1, and the vertical component of BA have to sum to 0. Okay, so that's how I handled that one. Oh, sorry, I left out those thousands up there, like you guys are hundreds. Guys, let me do that. Oh, actually, you know, that's an easier way to do that. Just sum it next. I didn't see that my first time through. Yeah, just sum it next. So we've got a plus 200 minus FBA times sine 53. That's what I got. Yeah, you probably. Yeah. Okay, that looks okay, everybody? Okay. So that one was really straightforward. This one is a little tougher. Unless we see something again that I've missed. I think I took a quick look to see how they solved theirs. Maybe we should take a quick look. Oh, I know they did pins. I didn't do pin method. I think it's about the same. Okay. First thing though, when pardon? It's not symmetric because the 5,000 is not. Yeah. No, it's, yeah. Okay, so the first thing I want to do is look at and realize that I do have to find F1 and F2. And then the second thing is if there is an F1 here at this point A, then this is not the way to do it, but I want to throw out something up there, so I'm gonna kind of broach this idea. If I look at pin A, I've got this F1, and then I've got force from AB, and I got the force from AC. Okay. Now, the force from AB, its Y component can balance that out. But it has an X component. And its X component is going to be balanced out by this FAC. So there's no way that the tension or the force, sorry, the internal force in AC can be zero. Absolutely no way. So that means I can toss this one and I can toss this one. Okay. The other two, I don't think that there's a good way to figure it out without doing some more math. Okay. All right, so the first thing to do is to go ahead and figure out what F1 and F2 are. And I think I summed moments around F2. Let's just put them in here. They're working on the steel bridge. Sorry, I stumped around H. I said F2. I meant H. So I'm going to have a minus F1 times 32. Did I do that right? It's been a long day for me too. Yeah, some way that just looked weird. Okay, and then a 5,000 plus 5,000 times 24 is equal to 0, and that gives me an F1 of, what did I come up with? I got 3750. I think that's them. Or does that sound like it's in the building? Okay. Some forces in the y direction to be 0 will give us F2. is gonna be, oh, what did I do? No, that's right. 1250, right? Yeah. Okay, so now we have this one and this one. Oh, let's put those in there actually. This is 3750. And this is 1250. Okay, cool. So now they did a pin analysis. I thought it was actually faster to do a section analysis. But we are, so I took a section right here. And I took a section right here and went for BB first. Okay. And we're going to need an angle. So what angle did I go for? Just out of kicks. I lied. You know what I did first? Yeah. And I did it via a section, but you could do it via a pin. If we did a pin analysis here, right? Pull that out. Let me do section. I have to go back and think through my head what the signage is for pins, and I don't have to do that for sections. So I'm going to make a section like that. This is 3750. This is going to be force FAC. This is going to be force FAB. And this angle right here is tangent of that angle. Is 8/3 over 8. So theta is at 18.4. Yep. Okay. So if I do a sum of the forces in the y, I got a plus 3750 plus FAB sine 18.4 equal to 0. That lets me figure out FAB. And I got got a minus 11,861. Okay, so it actually should be going in this direction. I'm going to come in and sketch that in. Okay. We actually should have guessed that from the beginning, right? If this is up, this should have been going that way. But now I can come in for my sum of forces in the X. So I'm going to have a minus FAB times, well, all of a sudden that's looking funky to me. Cosine 18.4. Sorry about that. Plus FAC. But I remember that this is 11,861, so I have 11,861 cosine 18.4 plus FAC is equal to 0, so I can figure out what FAC BD is. And I got 11,251. So I would go with A. I could go in and figure out BD, but I don't have to. And if I wanted to figure out BD, I just do the section and I do exactly what I just did. Or I have options. I got some of the forces and some of the moments. Yeah, actually, I just figured out there is a way you can do that in one step. If you actually drew that section and then took the moment around point B, that would drop out and you'd just be left with this and this. And so you could do it in one equation. It must be cutting.
Wouldn't BD cancel if you took them all around?
That's the idea, because if I'm looking for FAC,
Oh, okay.
I would pull FAC out immediately. Okay. Okay. Do you want to do another trust problem, or do you want to go on and come back?
These are basically like you do a method of section and a method of joints,
Yeah.
and it's just finding the little pieces and putting them together.
Yeah.
And then-
Go on to some of the other stuff. Okay. Let me look real quick in my notes, see if there was anything tricky on that one. Because I think you're right, Ashley. That was how I was looking at it. It was, yeah, I did it method of sections. And I know I spent time trying to think if there was a way to get that out easily. I had to use 3 equations. Well, I had to find the support reactions. I was looking at problem 2. Had to find support reactions and then I did 2 moment equations. I could not see a way to do that one easier. Anyway, you know what to look for for the easier ones, if you get a choice. Okay, cool. Pulleys, cables, and friction. So this one, it was somewhat a mixture of statics and back to physics, introductory physics. So let's look at the first one in these. Don't you love it? Block on an inclined plane. You still can't get away from that. Okay. So we have a block on the inclined plane. They give us the coefficient of static friction is 0.2. And they want to know approximately how much additional force F must be applied to keep the block from sliding down the incline. Okay, so the first thing to think about is which direction is the friction force. And if they're worried about it sliding down the inclined plane, and this is keeping it just so it doesn't slide down, so you would be thinking impending motion, then the friction force is uphill, okay? So the friction force is in this direction, and it is a static friction force, okay? Then I gotta come in and put my normal force and my weight force. I'll borrow this. And I'm gonna put them at this point just to help us with having everything at the same point, I guess. So my weight force axe straight down. Actually, let's go all the way. That's my weight force, and my normal force is perpendicular. Okay, so the next thing we want to look at is angles. And this is a little weird, but this is why I do it this way. This, I shouldn't say it's weird, but I don't know that a lot of physics people teach it this way. This right here is a right triangle. And so if that's 34, that's 90. This is 90 minus 34. That makes this angle right here 34. I think a lot of people use similar triangles. And I just draw that thing down and fake like it's a, I mean, it is a triangle, but it's a little weird because this is a force and these two things are distances. So this is 34 degrees. Okay. Then what I do is I'm going to actually rotate my free body diagram because it lets us look at all of our vectors a little bit more normally. So this is now going to be my X. This is going to be my Y. I'm going to come in and draw in a box. And we are going to have I'm going to put them in blue. We got a normal force up. I've got a force F. And I've got a friction force. Static friction force. And I have my weight force. There's my normal, and this angle right here is 34 degrees. Okay, and this looks a little bit less scary than having things on tilted axes. Okay, so I got to remember my friction force is going to be u sub F times my normal force. Okay. So I need to figure out my normal force first, and I can do that by summing forces in the y direction. So the sum of the forces in the y direction is equal to 0. That gives me my normal force minus my weight force, and I need the y component, so that is cosine 34 is equal to 0. And I told us it was a 2 kilogram block. So normal is going to be 2 times 9.8 times cosine 34. I got 16.25 for the normal force. Okay, so if the normal force is 16.25, that means my static friction force is 0.2 times 16.25. And that's going to be 3.25 newtons. Okay, hang on just a minute. Yes.
Why are you making the normal force by an angle?
No. The weight force was multiplied by cosine. So then the normal was, right, normal.
Oh, is that equal to?
Yeah,
okay,
so normal,
okay.
vertical, normal is only in the vertical, and I need the vertical component of the weight. Okay, thank you. Yep. Okay, so now I got to sum forces in the x direction. equal to 0. And obviously I have these two. So that's 3.25 plus F. And then I need the horizontal component of the weight force, which is going to be the sine component. So that's going to be, and I'm just going to put in the weight, 2 times 9.8 times sine of 34 is equal to 0. And I can solve for the force F. And I came up with 7.71. Any questions? Good? Okay. Ashley, okay? Okay. This little turkey is a sneaky one. And sorry, I was drawing on the thing at some point. Oh, the previous one, I don't know if there's any answers you can easily throw out. Guess I should have said that. This one, there are a few, or at least one, maybe two, I can't remember. Okay. So this one, there's a couple of things that are key in this one. It says the box has a uniform density and a total weight of 600 newtons. And it's suspended by 3 equal length cables. And then it says the intersection point is a 0.5 meter above the center of the box top surface. Okay. So if you think about this from a symmetry point of view, this cable here can't actually be carrying any of the load because it would need something from over here to balance it. So this is gone, and the only two that are carrying the load are FCE and FBE. Okay. Now here's where you can throw a few things out. If those two cables were exactly vertical, then they would each have to hold 300 newtons. Okay. If they're tilted, they're going to actually have a bigger tension than if they were vertical. So the ones you should be able to throw out right away is this one and this one. Okay. Now, how I looked at this is looking at it in this geometry was awkward. So what I did was I came in and looked at it along this, at this corner. And then these two forces would be coming up. So the way I kind of sketched it out was and then this would be the corner at A. And so my two cables are going like this. Okay, this would be corner C, bless you. This would be corner B. So this would be FCE, and this one would be FBE. Okay. And you know that the two of them are have to carry the same tension because it's a symmetric problem. So I need that angle. And this angle right here, theta. So I want to come back and think about that. I'm looking at this diagonal. Okay. So this length right here, that's the square root of 0.6 squared plus 0.4 squared. And I got that to be 0.721. Okay. I know this is half a meter here. So tangent theta is going to be a half meter divided by 0.721 divided by 2. And that gives me a theta of, I have 54.2 degrees. Okay, everybody follow my geometry? Because I was facing the board, not facing you. This diagonal right here, that's the line that I've got right up there. And then I'm looking straight on to this corner formed by that side. Okay. All right, once I've got that, then I can just take the two y components and set that equal to the weight. I'm summing forces in the y direction. So I've got 2 times, I'll call it FCE. And I need the vertical component, so I've got sine 54.2 is equal to 600. And when we solve for FCE, I get 370 newtons. Yeah.
Why is it the 600? So, like what you said, the 600 can't be, it cannot be 300 because they're acting at an angle. But when you're just solving for CE, would it only like, wouldn't the horizontal weight for CE only be 300? Like, I mean, I know it's not, but why isn't that equation set equal to?
I'm understanding part of your question, but not all of it.
So you have the two tables and
Right.
the 600 is acting on both of them, but we're just solving for the force in the y direction.
If I solve for the forces in the horizontal direction, I'm just going to get FCE equals FDE.
Right, but
I would get FCE times cosine 54.2 minus FEE times cosine 54.2 is equal to 0.
okay, so then why?
The way I've done this in the past, maybe this is a better way to do this.
Why isn't DE in the equation if you're solving?
Because this is FCE is equal to FDE.
Oh, okay, so that's what the 2 is.
Yeah, that's why the 2 is there.
Okay, sorry.
Yeah, no, that's okay. I knew there was something, I just couldn't see what you were asking. I argued it from symmetry, but you could do it mathematically to show that they're the same. Okay, does that make sense to everybody? Okay. Like I said, that was a bit of a stinker one. Next one is pretty straightforward. I don't know if we need to go through it or not. You're gonna draw a free body diagram for the knot at point A. And then do a sum of the forces Y, sum of the forces X. Did you want to go through that one, or are you okay with that one? All right, my free body diagram looks like this. Question. Let's see, this is 4, 3, and this one is 3, 4. So those are 3, 4, 5 triangles. So you're going to actually need to do 2 equations to do this one. If you do sum of the forces Y, you're going to have a 3/5 times TB. Here you're going to have a 4/5 times TC minus 100 equals 0. And then a sum of the forces X, you're going to have a 4/5 TB, and that has to be negative, plus a 3/5, 3/5 TC is equal to 0. And this one is probably where I would go. That's going to give you 3 times TC is equal to 4 times TB. And I can solve that for, I'm looking for B. So if I solve that for TC, I'm sorry, for, yes, for T, no, I want to solve for T, hang on, let me think here. If I solve for TC, then this will have only TBs in it. So TC is equal to 4/3 times TB. I take this and I stick it in here and I solve away. Actually, if you were even really clever, you might, no, you still have to do something like that. Look okay? Okay. The next one I thought we would do, because it's a pulley setup, and pulleys are a little different, and if you see what's going on, they're usually fairly straightforward to solve. And I don't know how to knock any of these out on this one either. This one is a bit of a stinker because you have this 1200 Newton item down here, but you don't know how the weight is distributed in it. So you can't say that this tension here is going to be the same as the tension here. Okay, so that forces us to start up here on this one. And so what we do is we do a free body diagram for pulley A. We just kind of come in and circle it. And so pulley A looks like this. Now, the other thing is for ropes, when they wrap around pulleys in these types of problems, the tension is the same everywhere in the rope. So I'm going to have a T upwards, another T upwards, and that means that this rope right here has to be 2t. Okay. Once I got that, that lets me move to pulley B. So I come over and look at pulley B, and pulley B has 2t upwards. Right, because this is the same rope. And then I have to figure this guy out, and if it's 2t and 2t up, that makes this 4t. Then I get down to pulley C. And pulley C, again, this rope here is the same, it goes all the way over. So this is 4t. 4t up, 4t up. That means this is 8t. And that means when I come to look at this load, I know this is 8t and I know this is 4t. So I get 12t is equal to 1200, and I get t is equal to 100 newtons. That kind of makes sense to everybody? You usually just have to start at one place or the other. You either start down here or up at the top. But when they, and I'm sure they've got this set up for if you started at the bottom, you do some things, you probably come out with one of those answers. But if they don't specifically tell you something in here that lets you think that this force and that force are going to be the same, you better not think it's the same. Good? Okay. Moving on to the next chapter. To centroids and moments of inertia. So for this, you need the tables. Some of the easy things you should probably just remember, like the 1/12 base height cube. But for circles and semicircles, I don't remember them. Okay, but this is we'll be looking at. Oh, I guess I should erase so you can see. The ones that get used the most, just so you know, at least in what I've seen in this one. Is this one for rectangles, and then circles and semicircles. Okay. And I realized this afternoon that they didn't have any distributed load practice in the statics. And I don't know if that's because they cover it in structures, maybe. I don't know. Okay, so we'll start with the first one. They're looking for the moment of inertia about the x-axis for the area shown. And what you have to remember is these formulas, and books always have different notation for this. So, and I should have looked to see what the manual did. But this, let me go back up to this figure. So here is the 1/12 base times height cubed. So that is the moment of inertia about the centroidal axis, which would be right here. It's not this one down here. It's this one, okay? So it would be around this axis. Now, a lot of times what they're asking us to do then is to find the moment of inertia around another axis. And so you always have to remember, you have to use I is equal to I centroid plus A times B squared, where this is the distance between the centroidal axis and whatever axis that you're asked to find the moment of inertia around. Okay? So frantic scribbling so well. Everybody good? Okay. So I like to set these up in table form when I solve them. So if I look at this one, I'm going to break this. It's a composite structure, so I got to break it into two pieces. And I would probably do the division here, and I call this piece 1, and then this piece 2. Okay? And moments of inertia simply add. So if I find the moment of inertia for this around the x-axis, and the moment of inertia of this around the x-axis, I can just add them up. So like I said, I like to build a little table. So here's, I put in the piece. I'll put in I centroidal. Then I put in how far it is to the axis that I want to find the moment around. And then I calculate the area. And then I do IC plus D squared area. Okay, so I'll start out with piece 1. It's going to be 112 times 1.5 times 4.5 cubed. Sorry, that's a little small, but that's how it's going to have to be. I have to make sure I got the right, okay. So I got 9.11. Now, again, it's pretty common to give these things in centimeters to the 4th, millimeters to the 4th. So there's no funky things with units in these things. I didn't see any problems where they were playing with units, yeah, giving it to you in one and asking for it in something else. Okay, so that is through this axis right here. So I need to know how far it is from the center of that rectangle down to the x-axis. So this would be 2.25 from here down to here. So this is 2.25. The area would be 1.5 times 4.5. Yep, 6.75. Okay, so this over here would be 9.11 plus 2.25 squared times 6.75. I got 43.2. Okay. For which one? I see. 112 times 1.5 times 4.5 cubed. I got 9.11. I just got 11.4. I got 9.11 there. Let's see if they did it. Oh, they did it. They did it slightly different way. Oh, that's not gonna work. 25. Well, I'm gonna go with your 11.4. Are you checking again?
I got 11.4.
Okay, let's go with your 11.4. What are you gonna get this sum to be? Okay. And here's to the fourth. All right, let's look at 2. So this is gonna be 112 times 7 times 3.5 cubed. Sorry. Yeah, no, that's right. I got 251. What the world did I do? I was really tired when I did these, but I came up with an answer that looked like theirs, so I went with it. No, I got their final answer for this one. Let me double check. But I did get their, oh, but it could be really balanced by, hang on a minute. 1 divided by 12 times 7 times 3.5 cubed. 25, okay? Maybe I just wrote it down wrong. I got 25.1. Okay. D is going to be from the center down to here. So I have 4.5 plus half of 3.5, 6.25. Area is 7 by 3.5. Which I got 24.5. That looks at least good. Okay, so we should have 25.1 plus 6.25 squared times 24.5. And I got 982. And they got 982. Yep. So then the moment of inertia for that composite is just those two things added together. That looks okay? Okay. X and Y coordinates of the centroid. Again, it's a composite structure. Now the centroid has to lie on a line of symmetry. So the centroid has to be on a bisector for this one. And that would mean if this is 4 and that's 4 and that's 4, then it has to lie on x equal to 6. Okay, so that automatically tosses this guy out. You could probably guess, I think it's, well, I don't know. The other three, it's hard to pull out. I might guess that it didn't lay out to 8, but I think that would be a guess. So centroids, the formula for centroid is x bar. This is the formula we use in the statics book. The sum of, I call it x tilde times the area divided by the sum of the area. Okay, so x tilde, that is the centroid for the individual piece. Okay, so again, I'm going to build up a table. And we figured out where x bar is, so we actually need y bar. Sorry, y tilde, a over the sum of the a's. Okay. Yeah. It has to be on that symmetry, line of symmetry. Okay. Okay, so again, we're going to build something up. I put in y tilde and then the area. And then y tilde times the area. So I'll call this piece 1 and this piece 2. So y tilde would be, where is the centroid of, I'm sorry, did my division on it like that, like I did last time. Where is the centroid for this piece? It would be right here at 4. The area is 4 by 8. And then I'd have 4 times 32. Okay. Piece 2, the centroid would be right in the middle. So I have my 8 plus my 2 is 10. The area is 4 times 12. And so this is going to be 10 times 48. Okay. Now what I need to do is sum the last 2 columns. So 32 and 48 is 10 is 80. And then whatever that turns out to be. Let's flip my page. I got 608. Okay, so that means y bar is going to be 608 divided by 80. Which is 7.6. Okay.
Why do we choose the center piece?
Yeah, the centroids are just the center pieces. Sorry, if you were to look at the what you would consider the area center of that thing. Yeah. And some of the other problems in that section, they just played around with some of the wording. I don't know if I put them in here. We can talk about them. Oh yeah, holes are negatives. Okay, so if you get a hole, then the area is considered negative. So you would put a negative in here. Well, like if I were doing this and I did that hole, then my area for that is a negative value. Okay, but like this one is a kind of a weird thing with everything they gave you. We won't go through it for the math, but It tells you the senatorial moment of inertia of area A2 with respect to the composite senatorial x-axis is 73.94. So they figured it out wherever this senatorial x-axis was. I think they gave it to you. This is 4.79. So they gave you the moment of inertia for this around that axis. And they gave you the moment of inertia of this around that axis. And then they asked you for the moment of inertia for the whole piece around that axis. So you have to come in and figure out the 1/12 base times height cube, and that's going to be around this axis. So the D would be the D for this minus that. So it would be 10 minus that 4.7, sorry, 5 minus 4.79. So they're just plain, did you understand everything that they gave you? You still have to do some calculation, but it's not. Yeah. So actually, I think the calculation you have to do is pretty minimal, but you have to pay attention to their words. Is that a good place to stop? My brain is fried. I can imagine your guys' brains are fried too.
Thank you.
You're welcome. Good luck to everybody.